Hello students, welcome to Code to Serve Academy. Today we will study about properties of rational number. So, what do we mean by properties of rational number? So, what are the things which rational numbers follow that are included under properties of rational numbers? The first property which we are going to study is the closure property. The first property is closure property. So, what is closure property? If we are provided two rational numbers and they are operated with fundamental operations, what are our fundamental operations? These are addition, subtraction, multiplication and division. So under these fundamental operations, if two rational numbers are operated and we get the value as a rational number, then we say that the rational numbers follow closure property. For example, let us suppose that our first rational number is a upon b, okay, and the fundamental operation is addition. When it is operated with a number that is c upon d, another rational number, if we get a value that is e upon f, another rational number, then we say that rational numbers follow closure property, or rational numbers are closed. So to understand this, let us take an example. For example, if we take our a by b as 1 upon 2 and our c by d as 1 upon 3 and we add these two numbers, what we will get? First of all, we will take LCM. LCM of 2 and 3 will be 6, and in the numerator we will get 3 plus 2. That means the value will be 5 upon 6. So this was a rational number. This was a rational number, and again we got another rational number. So on operating two rational numbers, we are getting another rational number. Similarly, like this, if we take any two rational number and we operate them with addition, then we will get another rational number. So by this way, we can say that under addition, rational numbers follows closure property. Similarly, for subtraction, let us suppose we are subtracting these two numbers. So what will happen? Again the LCM will be 6, and in the numerator we will get 3 minus 2. That means the value will be 1 upon 6. Now also 1 upon 6 is a rational number. 1 belongs to the set of integer, 6 belongs to the set of integer, 6 is not equal to 0. So we can say that this is a rational number. Also P and Q are co-prime. 1 and 6 are co-prime in nature. They have only one factor, that is 1 itself. So we can say that this is also a rational number. So we operated two rational numbers with the fundamental operation subtraction and we got another rational number. Hence we can say that rational numbers are closed under subtraction. Now moving to our next part. If we take the fundamental operation as multiplication, then what will happen? So if we take 1 by 2 and 1 by 3 again, and the operation we take as multiplication, then the value will be 1 upon 6. The numerator will be multiplied with numerator and the denominator will be multiplied with denominator. So we will get 1 upon 6. Here also we see that it is a rational number. So we can say that rational numbers are closed under multiplication. For division, the same thing happen and we will get, since we know that division is the reciprocal of multiplication. So if multiplication is happening, we can say that division can also do the same thing. So if we operate these two rational numbers under division, what we will get? We will get 1 by 2 and this 1 by 3 will be 3 upon 1 on reciprocating, and this division symbol will be get converted into multiplication. So we will get the value as 3 upon 2. Now this was a rational number, this is a rational number, and we again got a rational number. So we can say that these rational numbers are closed under division also. So for any fundamental operation, we can say that rational numbers are closed. Okay, they follow closure property. Now moving to our next part, the second property. The second property is associative property. What is it? Associative property. So to understand associative property, what we will need? We will need minimum of 3 rational numbers. We will need minimum of 3 rational numbers. It can be any of the rational number. Let us suppose that the rational numbers are 1 by 2, 1 by 3 and 1 by 4. To understand the core concept behind this, let us suppose that we are having 3 rational numbers. The first one is a upon b, the second one is c upon d, and the third one is e upon f. Let us suppose our basic fundamental operation which we are using here is addition. Also, what we are going to do, we can add these numbers using parenthesis. So we can use parenthesis in these two numbers, or we can use this the parenthesis with these two numbers. So what we have to do, we have to check that under this parenthesis the value is equal to under this parenthesis or not. We have to check that this value is equal to this value or not. If this value is equal to this value, then we can say that the rational numbers which we are taking are associative in property. Okay, are associative under addition. This will be of 3 rational numbers. So if we take any 3 rational number, we will get some values. We will try to find out for some more 3 rational numbers, and we will check out that are they follow the same condition. If they are following the same condition everywhere, then we can say that they are following, every rational number is following associative property under that operation. So let us suppose that these are 3 numbers which we are taking. These are easy numbers which we can take, hence I am taking these things. Okay. Now for LHS part, this is our left hand side. So we are taking this part first. So this part is under parenthesis 1 by 2 plus 1 by 3 plus 1 by 4. It is. Now we have to solve the bracket first. The LCM of 2 and 3 will be 6, and the numerator will be 3 plus 2, and it will be added with 1 upon 4. Now we will get the value as 5 by 6 plus 1 upon 4. We again take LCM. So what will be the LCM of 6 and 4? It will be 12. So what we will get? The LCM of 6 and 4 will be 12. So what we get? It is 12. So 6 when multiplied with 2 will give 12. So 5 will be multiplied with 2 and we will get 10. It will be added with 4 when multiplied with 3 will give 12. So 1 will be multiplied with 3 and it will be 3. So what we will get? We will get 13 upon 12 as the LHS. Now we will move towards RHS part. We will move towards RHS part. What is our RHS? Our RHS is 1 by 2 is added with under parenthesis 1 by 3 plus 1 by 4. So this is our RHS. We have to find the value of this. So 1 by 2 will be added with the LCM of 3 and 4 will be 12, and we will get 4 plus 3 in the numerator. So the value will be 1 by 2 plus 7 upon 12. Okay. So the LCM of 2 and 12 will be 12. We will get 6 plus 7 in the numerator, and in the denominator we will get 12. So what will be the value? The value will be 13 upon 12. So what we got? Under addition, these three rational numbers followed associativity because the LHS part and the RHS part are same. But if we say that for another three rational numbers, is the condition is valid? If we take some more rational numbers, some more three rational numbers, that is, let us suppose we have taken 2 upon 3, 4 upon 3, 5 upon 3, then this condition is valid or not? So when we check on every rational numbers, whatever it is, we will see that this condition is always followed. So we can say that rational numbers follows associativity under addition. Okay. Now moving to our next part, associativity under subtraction. Associativity under subtraction. Under subtraction. So first of all, we have to recall what we have to do in this scenario. So we are having three rational numbers. Let us suppose that the rational numbers are a upon b, c upon d and e upon f. Also, let us suppose that these numbers are here also. Now, what we have to do? We have to use the operation subtraction since we are moving towards the subtraction phase. So, this will be the representation. First of all, we have to take the parenthesis in the LHS as this, and we have to take the parenthesis in the RHS as this. So, we have to check this is equal or not. This LHS is equal to RHS or not. So, let us check. Let us suppose our first three numbers, that is 1 by 2, 1 by 3 and 1 by 4 for LHS. For left hand side, when we are subtracting these three numbers under the parenthesis of first two numbers, what we will get? We will get the value as the LCM of 2 and 3 will be 6. This value will be 3 minus 2 minus 1 upon 4. So, this will be the value. On solving this, we will get 1 upon 6 minus 1 upon 4. So, we will get, we know that LCM of 6 and 4 is 12. So, we will get 12. So, the value in the numerator will be 2 minus 3. So, we will get minus 1 upon 12 here. We are getting minus 1 upon 12 here in the LHS part. On the RHS part, if we solve, what we will get? So, this will be 1 by 2 minus 1 by 3 minus 1 by 4 and these two will be under parenthesis. So, what we will get? This will be 1 by 2 minus LCM of 4 and 3 will be 12. So, it will be 4 minus 3 in the numerator and the denominator will be 12. So, we will get 1 by 2 minus 1 upon 12. So, we will get 2 and 12 LCM as 12. So, it will be 6 minus 1. It will be 6 minus 1 in the numerator. So, we will get 5 upon 12. So, we are getting that our LHS is minus 1 upon 12 and our RHS is 5 upon 12. So, these two values are not equal. So, if we say, whenever we say that a person is saying many true things, but if the person is saying one false thing, then the condition is always getting false. We say that the person is liar. So in here also, if we are getting any condition where LHS is equal to RHS, but only one condition we are getting that LHS is not equal to RHS, then we will say that in whole scenario we can say that it will not follow associative property. So we can say that in rational numbers under subtraction associativity is not followed. You have to make it a note. Under subtraction associativity is not followed for rational numbers. Okay. Now we will move towards associativity under multiplication. Associativity under under multiplication. So what is the concept behind this? It will be same. We are having three numbers A by B, C by D and E by F on both sides. A by B, C by D and E by F on both sides. And we are operating with multiplication. This is our fundamental operation. So we are using parenthesis in the first two numbers and the parenthesis in the second two numbers on the RHS. We have to check that these two LHS and RHS are equal or not. Okay. So let us take the same example. We are taking 1 by 2, 1 by 3 and 1 by 4 and we are multiplying, and for the LHS we are having parenthesis under first two numbers. So we will have to solve it. So on solving the bracket part, what we will get? The numerator will be multiplied with numerator. So we will get 1 upon 6 and the denominator will be multiplied with denominator. So overall all value will be numerator of the overall value of the numerator will be 1 and the overall value of the denominator will be 6. That means it will be 1 upon 6. It will be multiplied with 1 upon 4 and we will get 1 upon 24. Okay. On RHS part, what we will get? On RHS, we will get 1 by 2, 1 multiplied with under parenthesis 1 by 3 and 1 by 4. What we will get? 1 by 2 multiplied with 1 upon 12. Numerator will be multiplied with numerator and the denominator will be multiplied with denominator. So what we will get? We will get 1 upon 24. So we are getting that LHS is equal to RHS. Similarly, if we take some more three rational numbers again and again, we will get this property is always followed. The LHS will always be equal to RHS. So we can say that associativity is followed by rational numbers under multiplication. So what is the remaining? What has been left till now? The left part is associativity under division. So I am giving it as a homework to you. You have to find out whether associativity is followed under division or not. Okay. Now moving to our next part. The next part is insertion of n numbers of rational numbers between any two rational number. Insertion of n number of rational numbers between any two rational number. Let us suppose there are some more properties of rational numbers which are required to understand, but I know that you have understood it better in class 8. The properties are distributive property, the properties are existence of identity and existence of inverse. So that is why I am not providing you here, because the questions are not related to class 9. It is related to class 8 for that type of topics. So I am not concluding it here. Okay. So what I am going to make you clear is representation of any two rational numbers on number line first, and how will we insert n number of rational numbers between any two rational numbers. So our topic is insertion of n number of rational numbers between any two rational number. So this is our real number line. We know that rational numbers are always represented in real number line, and the real number line is represented with this R. Okay, this first line is bold. Okay, so we are having two rational numbers. First of all, we are having two rational numbers. Let us suppose that our first rational number is A and the second rational number is B. So to represent anything on number line, we have to mark which one is smaller and which one is greater. So we have to assume which one is smaller and which one is greater if it is an arbitrary number, or if it is provided that the value of A is this and the value of B is this, then we will find out the value of A and B. Let us suppose that the value of A is 1 by 2 and the value of B is 3 upon it. So first of all, what we will do, we will find out the value of A, it will be 0.5. We will find out the value of B, it will be 0.3 something. So which one is smaller? 3 by 8, and which one is greater? 1 by 2. Similarly, we have to assume for arbitrary cases which one is smaller and which one is greater. Let us assume that A is less than B. So the lesser part, which is A, will always be in the left side of the number line. It will always be on the left side of the number line, and the B will be always on the right side of the number line. Okay. So what we are going to do, we have represented A and B on the real number line. Now we will require that we can insert, we have to find out that how we can insert n number of rational numbers between this A and B. Okay. So let us think. Let us think that we are going to provide one rational number between A and B. We are first going to provide one rational number between A and B. So how can we do this? We know that, let us suppose that our number is 1 and 2. That our number is A is equal to 1 and B is equal to 2. So let us think what will be the value of A plus B upon 2. What will be the value of A plus B upon 2? So the value of A plus B upon 2 will be 3 upon 2. Is it correct? And 3 upon 2 is 1.5. 3 upon 2 is 1.5. So where will 1.5 lie? It will be in between A and B. It will be in between A and B. So we will get 1.5 in the middle of A and B. That is, if we have taken A as 1 and B as 2, we will get 1.5 here. So we will get A plus B by 2 here. So we have now we will check A plus B by 2 is a rational number or not. So we have got 3 by 2. Is 3 belongs to the set of integer, 2 belongs to the set of integer, and 2 is not equal to 0 also. Also 3 and 2 have no common factors other than 1. So we can say that between A and B, we have inserted one rational number, that is A plus B upon 2. Is it true? So now what we will do? We have inserted one rational number between A and B. Similarly, between this and this, between this and this, we will insert one more rational number. We can insert between these two rational numbers in the midway. We can insert one more rational number, and this, let us suppose that this is something called C. Let us suppose that this number is C. So this C number is also between A and B. So we have inserted two rational numbers between A and B. Also, if we insert one more rational number between A and C, then what we can say that we have inserted three rational numbers between A and B. Similarly, between A and D, if we insert one more rational number, then we will get one more rational number between A and B. Similarly, through continuing this process, we will get infinite number of rational numbers between any two rational numbers. Is it okay? So this is the basic concept. Okay. Now we will move towards the decimal expansion of any number. Okay. The decimal expansion of any number. What is decimal expansion of any number? So it is the decimal representation of a number. Let us suppose that 1 by 2 is our number. So the value of 1 by 2 will be what? It will be 0.5. It will be 0.5. When 1 will be divided with 2, what we will get? We will insert a 0 and a point here. So on multiplying with 5, we will get 10. So the value will be 0.5. So this is a decimal representation of a number. Okay. Similarly, if we are saying that a decimal representation is like 0.33333333 and continued up to so on. Okay. So what we are getting? We are getting 0.3333333333 continued up to so on. So there can be a case in which this type of decimal representation may occur. For example, if I am saying that the number is 10 upon 3, the number is 10 upon 3, what we will get? We are dividing 10 with 3. So it will be like 3.333. So the number will be 3 3s are 9. We will again get 10. For 0 we will provide point. So it will be 3.3. We will again get 10 and this will be continued. So what we are getting? We are getting a decimal representation in which numbers are repeating itself. Numbers are repeating itself. Now we have to think that the numbers can repeat on the first phase or on the second phase or anywhere in between these numbers. For example, let us suppose that I am providing a number decimal representation as 0.54545454 continued up to so on. So this is also a case in which the repetition is followed, but it is followed between 2 digits after a decimal point. Okay. So this can also be the case in which repetition is followed, but the decimal representation or the decimal number is never ending. Okay. Also, let us suppose that there is a decimal representation as 0.010110. Okay, and this one is continued 010110, 010110. So this is going to be continued. So this can also be the case in which some pattern is shown between the decimal numbers, the decimal digits of that decimal representation. So what I am trying to say कि हमारे पास कुछ ऐसे नंबर्स हो सकते हैं डेसिमल रिप्रेजेंटेशन में जो क्या हो खत्म हो जाए डेसिमल के बाद कहीं पे भी, जैसे कि 0.5 ले लेते हैं, 0.65 ले लेते हैं, 0.345 ले लेते हैं. तो ये सारे नंबर्स क्या हो रहे हैं आफ्टर अ सर्टेन इंटरवल ऑफ टाइम ये एंड कर जा रहे हैं. कुछ नंबर्स ऐसे भी हो सकते हैं जो डिजिट के बाद, जो डेसिमल के बाद कंटिन्यूअसली रिपीट करे. कुछ नंबर्स ऐसे भी हो सकते हैं जो डेसिमल के बाद कंटिन्यूअसली रिपीट ना करे, एक सर्टेन इंटरवल के बाद रिपीट करे, जैसे 54545454, जैसे 0101110, 01110110, इस तरीके की रिपीटेशन हमें देखने को मिल रही है. तो ऐसे भी डेसिमल रिप्रेजेंटेशन हो सकते हैं, या तो फिर एक ऐसा भी डेसिमल रिप्रेजेंटेशन हो सकता है, एक ऐसा भी डेसिमल रिप्रेजेंटेशन हो सकता है 0.01 001 0001 00001 एंड कंटिन्यूड अप टू सो ऑन। मतलब क्या कि ये डेसिमल रिप्रेजेंटेशन जो है कभी खत्म नहीं हो रहा है, ये कंटिन्यू ही चलता रहेगा। ये भी देखिए कंटिन्यू ही चलता जा रहा है, ये भी कंटिन्यू ही चलता जा रहा है, ये भी कंटिन्यू ही चलता जा रहा है, ये खत्म हो जा रहा है कहीं पे जाकर के। तो हम लोग को क्या देखने को मिल रहा है, हम लोग को देखने को मिल रहा है कि डेसिमल रिप्रेजेंटेशन या तो डेसिमल के बाद एक सर्टेन इंटरवल के बाद खत्म हो जाएंगे, या तो फिर नहीं खत्म होंगे। हमें दो केस पहले मिले, और जब नहीं खत्म होंगे तो हमें दो केस मिल रहे हैं, या तो उनकी डिजिट्स जो है डेसिमल के बाद एक सर्टेन इंटरवल ऑफ टाइम के बाद रिपीट करेगी, या तो फिर नहीं रिपीट करेगी। जैसे कि अगर हम लोग पाई का वैल्यू ले लें, पाई का वैल्यू क्या होता है 3.14 एंड कंटिन्यूड अप टू सो ऑन। जैसे कि मान के चलिए इसके आगे के नंबर्स हम एज्यूम करते हैं कैसे है 3 2 5 4 6 9 8 7 2 3 1 8 6 डॉट 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 कंटिन्यूड अप टू सो ऑन। तो इसमें कोई रिपीटेशन हम लोग को देखने को नहीं मिल रही है। तो जब कोई ऐसा डेसिमल रिप्रेजेंटेशन हो जिसमें डेसिमल के बाद नंबर्स जो है कंटिन्यू चलते जाए, कभी एंड ना हो, और क्या हो साथ ही साथ कोई रिपीटेशन फॉलो ना करे, तो वो भी हमारा एक केस हो सकता है। तो हमने क्या देखा, अभी तक हमने देखा कि हमारा जो डेसिमल एक्सपेंशन है वो हमने देखा कि दो तरीके के हो सकते हैं। ये कितने तरीके के हो सकते हैं, दो तरीके के। पहला जो तरीका है वो है, द फर्स्ट टाइप इज टर्मिनेटिंग डेसिमल एक्सपेंशन, and the another one is non-terminating decimal expansion. So for terminating decimal expansion we have seen the examples as 1 by 2, that is 0.5. Let us suppose that 0.65, 0.385. So these are the numbers which are terminated after a certain interval of time after decimal point. Okay, and there are some numbers which are never going to be repeated, never going to be repeated, never going to be repeated, and is never ending. Also there are some numbers which are repeating itself after a certain interval of time from decimal and are never ending. So these are the cases for non-terminating decimal expansion. So we will get two more types of non-terminating decimal expansion. We will get two more types of non-terminating decimal expansion. The first one is non-terminating recurring decimal expansion. Non-terminating recurring decimal expansion. And the second one is non-terminating non-recurring decimal expansion. Okay, so what are the examples of non-terminating recurring decimal expansion and non-terminating non-recurring decimal expansion? Here non-terminating means never ending, and recurring means repeating. So the number will be, the decimal representation will be never ending and will repeat itself after a certain interval of time. But for non-terminating, non-recurring numbers, the number will be never ending, the decimal expansion will be never ending, and it will never repeat itself after a certain interval of time. Okay. So for non-terminating recurring, we have seen the example such as 0. It was 3.33333 continued up to so on, or 0.54545454 continued up to so on, or 0.54255425 and continued up to so on. So these are the cases of non-terminating recurring decimal expansion. And for non-terminating non-recurring decimal expansion, the examples are like 0.01001, 0001, 401 and continued up to so on. So there are no repetition in between the number, in between the digits after decimal point, and also the number is never ending. So the never ending number and never repeating numbers for a decimal expansion are termed as non-terminating non-recurring decimal expansion. Okay. So this is the case. Now we will find out which one is a rational number. We have got decimal expansion. We know that the rational numbers can be expressed in the form of decimals also. So we will find out which decimal expansion is a rational number. We will find out either is terminating decimal expansion a rational number or not, is non-terminating recurring decimal expansion is a rational number or not, is non-terminating non-recurring decimal expansion a rational number or not. Okay. So what we are going to do, first of all, we will check for terminating decimal expansion and non-terminating recurring decimal expansion. So it is for your note point that these two is always a rational number. I will now prove how it is. Okay. So let us suppose that the number is that the rational number that the number is that the decimal expansion is terminating. Our first case is that the decimal expansion is terminating. Case 1. So one example for this is if x is 0.5, it has been ended after after the decimal point. Okay, so we can write this 0.5 as 0.5 upon 10, that is 5 upon 10, that is equal to 1 by 2, and 1 by 2 is a rational number. So we have seen that this terminating decimal expansion is now a rational number. Now let us suppose that we have another terminating decimal expansion, that is like 0.365. So how can we say that this number is a rational number, or this decimal expansion is a rational number? So what we will do? We will try to multiply the numbers with 10, or we will simply divide the number like this. After the decimal we are having 3 digits, so on removing this decimal, we will get 10 to the power 3 in the denominator. So we will get the value as, the simpler value of this rational number will be 5. We know that these two numbers are both divisible by 5, so we will try to divide it by 5. So our numerator will be 5 multiplied with 6 will be 30, 5 multiplied with 7 will be 35, and it will be 1 on the carry part, so we will get 15. So 5 when multiplied with 3 will give 15. So 365 when divided by 5, it will give 73. Also 1000 when divided by 5 will give 200, that is 5 2s are 10 and 0 0. Okay. So now this is the number which which cannot be subdivided into simpler fraction. Okay. So we can say that this terminating decimal expansion is now again a rational number. So through this, if we take any terminating decimal expansion, whether it is like 0.4874, it will again be a rational number. So any terminating decimal expansion will be a rational number. Now we will move toward our case 2, that is the decimal expansion is the decimal expansion is non-terminating and recurring. Non-terminating and recurring. Okay. So let us see. Let us suppose that x is equal to 3.333333 continued up to so on. Okay. So our first thing is how to represent. We have to know how to represent non-terminating and recurring decimal expansion. So whenever a number is like this, we represent the number as, after decimal point, we have to find which number is getting repeated. Okay, which digits are getting repeated. So we see here that 3 is getting repeated. We see here that 3 is getting repeated. So we will mark this 3 as one digit and we will make a vinculum or a bar over 3, so that it means that this 3 after decimal point is going to be repeated for infinite number of times. Okay. So this x can also be represented as 3.3 bar or 3.3 vinculum, or it can also be represented as 3.3 dot. Okay. Now let us suppose that we have another number, that is, first of all I have to write it so that you get the note of it. Let us suppose another number is y, which is like 0.54, 54, 54 and continued up to so on. So what we are getting, these two digits after decimal point are going to be repeated. So what we will do, we will make a vinculum over 54. Okay. So it will be like, it can also be represented as 0.54 and above 5 and 4 there will be points. So this is the second example. If there is our third number, let us suppose that the number is 0.5478, 5478, 5478 continued up to so on. So what we are getting? We are getting 5478 as the repeating factor. So how we will represent 0.5478 and we will mark a vinculum over 5478. Okay. Or we can represent it like 0.5478 and we will mark 2 points over 5 and 8, so that we can say that these 5478 are going to be repeated infinitely. Okay. So this was the representation. Now we have to find out that this decimal expansion, this non-terminating recurring decimal expansion, is rational number or not. So let us take our first example. Our first example is x is equal to 3.33333 continued up to so on. So on multiplying with 10, what we will get on both sides? We will get, this point will be shifted here. So we will get 33.3333 continued up to so on. So let us suppose that this was my 1 and this is my 2. So our main aim is to make the digits after decimal point a repeating factor, okay, or the digits after decimal same as the above part. So in the above part, what we are saying, the digits are 3 continued up to so on, and also in the second one we are getting the digits after the decimal are 3 continued up to so on. So what we can do, we can subtract this from this, we can subtract x from 10x. So subtracting 1 from 2, what we will get? On subtracting 1 from 2, we will get what we will get. So first of all, take the LHS part. This will be 10x minus x. 10x minus x will be equal to, our this part is 33.3333 continued up to so on, minus our first part is 3.3333 continued up to so on. So this part and this part will be vanished. So what we will get on subtraction, we will get 10x minus x will be 9x. 9x will be equal to 33 minus 3. That means it will be 30. So our x will be 30 upon 9, which is equal to 10 upon 3, which will be equal to 10 upon 3. So it is a rational number. It is a rational number. So we have proved that any non-terminating recurring decimal expansion is a rational number. Now let us suppose our second example was 0.54 Vinipula. So here the question is, y is equal to 0.54 Vinupulum. So we can represent it as 0.5454 continued up to so on. So what we have to do, we have to make this 54 as the common part. So to make again 54 in the decimal part, we have to multiply it 100 times. So on multiplying 100 times, let us suppose this is our 1. On multiplying 100 times, both sides, what we will get? On multiplying with 100, both sides, we will get 100y equals to, this decimal will be shifted here, so it will be 54.545454 continued up to so on. So what we have done, we have tried to make 545454 infinite times as the common part from decimal. Okay, so let us take it as 2. So subtracting 1 from 2, we will get, on subtracting 1 from 2, on subtracting 1 from 2, we will get, what we will get, we will subtract this 100y with y. So we will get 100y minus y will be equal to 54.545454 continued up to so on, minus 0.545454 up to so on. So we have made this part and this part as the common part. So after subtraction, this will get vanished. So what we will get? We will get 99y. We will get 99y will be equal to 54 minus 0. That means it will be equal to 54. So we will get y as 54 upon 99. We will get y as 54 upon 99. So the value of y will be, we know that the sum of 5 plus 4 is 9. So it will be divisible by 3, and 9 plus 9 is 18. So it will also be divisible by 3. So we can divide the both the numerator and denominator with 3. So we will get 3 ones are 3, 3 eights are 24, 3 threes are 9, 3 threes are 9. Now again also both can be divided by 3. So we will get 3 6 are 18 and the denominator will be 11. So the overall value will be 6 upon 11. So the value of 6 upon 11 will be 54.545454 continued up to so on. Okay. So this is again a rational number. So like this way, we can say that every non-terminating recurring decimal expansion is a rational number. This is all for today. On the next chapter lecture, we will deal about irrational numbers.